Hello MTV, and welcome to my presentation of my OPL exercises. So I did two exercises. I did the basics one and I did the ISWIM interpreter, and I get into more depth with the ISWIM interpreter, but the first one I want to go over is the basics exercise. So a lambda is essentially a function call where work has to be done, and so that is representative of where code function calls the logic of code function calls, where they come from. And this is an example of some of the ways you can do multiple function calls to represent lambda calculus and work being done, and how that is prominent. So we take this list of numbers, right, 1 through 6, and that's the only input we're going to get with actual real numbers. So when we work with these numbers, we won't have to keep entering them in or doing specific evaluations with them. We can use them as representations of these numbers. So that has to do with church encoding, where the introduction of a function being able to do something with a representation of a number instead of an actual number has added a lot of variety and a lot of power to the way people program today. So this is pretty simple and straightforward. We take this list of numbers, and I have an identified lambda, which is somewhere that work is going to need to be done. So it's like a function call. And this first one, called list sum, just takes a sum of the list. So it's 1 plus 2 plus 3 through 6, and that's very straightforward. And a couple lines down here, I set it equal to a variable called sum, and then I print that sum. So the print is just another function that, just for the sake of us being able to look at this. But so as you can see on the bottom here, I have these printed in kind of an odd order, but the second number is 21, which just added all the numbers together. So it's really straightforward lambda function to be able to get the grasp of being able to take in a number, have it church encoded, and then being able to work with it. So another thing that's possible is a function like this one even uses less syntax. I call it raised to power, and essentially it takes the first index and raises it to the first power, second index to the second power, third to the third power, and so on. The way I have it set up is if I change that number 3 to number 5, it would actually raise it to the 5th power. But just for the sake of keeping everything in order, I numbered my list like that. So as you can see, you can pass in the whole list, which is another representation of not having to enter in all these numbers and do all this extra work individually. And all I did was I called print, raised all these numbers to the power, and that was very straightforward. So there are different things you can do with lambda calculus, and they obviously get a lot more complicated. I didn't delve too deep into crazy functions, but this is an example of a simple comparison. I can say, this is a function lambda. If x is greater than 10, return. It's going to return true if it's greater than 10, or false if it's less than 10. And I have two examples of 8 and 18. You can see below over here. I don't know if you can see my cursor too well, but they return false and true accordingly. So theoretically, you could take those results of those functions and say, if false, then do something else in the next lambda, or if true, do something in the next lambda also. So this last one is just a quick representation of that, where I have a function that I called add 5, because what it does is it adds 5 to a number, and I gave it the argument 4. So this is not from our list of numbers, so we do have to input this, but 4 in this add 5 function is going to be represented over here by x, so at x plus 5, and that gets us our answer, which is 4 plus 5, which you can infer is 9. And I actually printed that below just to prove that it works. And then you take that, and I did a multiply by 2 function, which takes the same logic, and you can really put the pieces together as to what that does. And then we get our original 4, and we called 2 functions, and it gets us 9, and then 18 is our final answer. So what I have here in the comments, and I will uncomment it to make it a little bit more visible, is I have 2 examples of what I believe those lambda expressions are representative. So we have a lambda x that takes, it's going to take 2 times an x. But we can't do that first because inside of that, because we can't substitute x yet because there's a nested lambda inside of that. So we take this lambda y, and this is going to be where we do the work from first. So this is really simple, and I'll go over in detail more how this works in my next exercise. But you have 4 substituting the y, so you get 5 plus 4 is going to equal this first lambda. So that breaks down to this line, lambda x, and now we have 2 times x, which is going to be substituted by 9, which gets us our answer of 18, which I'm going to comment these in again and just run the program just so you can see that it actually did something and gets us all these answers, and that is 18. So that was my introduction to the lambda calculus through this exercise, and it went pretty well. I feel like I am able to determine where the function calls are coming from, how to represent data appropriately, how to work with encoded numerals, and such forth. So this is the ISWIM interpreter that I came up with. Disclaimer, I have a lot of print statements that I didn't get rid of because I didn't feel like it mattered that much, and they kind of at certain times can help break down the answer to a little bit more specific if we decide to look for it. So what this ISWIM interpreter does is it's going to take a ISWIM function similar to what we just worked with, and it's going to parse through it, do the work in the appropriate spots, and get the answer. So I'm not going to start with this because this is what we'll get to. What this program is able to do is it's able to read from this text file, and it can take simple operations like 9 plus 8. So this is, we have an operator, then a 9, then an 8, and that is going to get us an answer of obviously 17. So if I run this, we're going to get some little bit of extra output, but my final answer of 17 takes my first argument 9 and my second argument 8. So I'll detail how that works. So towards the bottom here, sorry about all the scrolling, where are we? So first I open up the file and I read through it, and then I'm representing lambdas with the character L because I couldn't get the actual lambda character. So this is not a lambda. So this is just an explanation of how small step semantics work. So we're going to go into this section where we didn't find a lambda. It's going to reverse through the input. So it's going to look from the right to the left until it finds the first left parenthesis, because that will be the rightmost work that we have to do. So this isn't nested, so there's only one computation to do, so that should be pretty straightforward. So then it's going to call this guy read input. And so what read input does is, it's up here. So this is actually where it's going through and finding the leftmost parenthesis. And so if it were nested, which I'll get to it later, it would save different sections of the input in different spots. So I would save what was before the parenthesis and what was after the parenthesis, because that was the best way I could parse through it. It probably isn't the most efficient way, but it worked for my purposes. I find the operation. In this case, it was a plus operator, and I just have a little, a few logs, whatever. And then I'm saying, so if we have a digit, I'm going to save, there are going to be 2 arguments because that's all that this can handle. It has a plus operator, a first argument, and a second argument. In this case, because it's small step semantics, they will just be digits. So I had something print out, and you can even see the first argument, this guy right here, is printed towards the bottom. First argument is 9, second argument is 8. It's a plus operator, so we just did a simple addition. And that returns us our answer, and it also returns us what is left in that lambda expression. I will get to that shortly because we will work with that very soon. So that's how we got our final answer of 17 with that very simple 9 plus 8. So let's say I took that 9 plus 8 and I wanted to make it a 9 plus, let's do a minus 7 minus 5, and let's close that parenthesis. So this should do 7 minus 5 is going to equal 2. So this should be 9 plus 2, which should get us 11. So I'm going to just save this guy because that's all we want for the input. And I'm going to run this, and it did work. So it did what I detailed earlier, which was, so it took the 7 minus 5. It went back and found the leftmost parenthesis, found 7 minus 5, got an answer for that. And it returned the answer, and it returned the before smaller operation, which is just what's left of that particular operation. And then if we go back to our main, or whatever is main in Python, this was my first experience in Python also. And then so because I called this in a for loop, I just go back and look for the next leftmost parenthesis. And I had a little bit of trouble parsing through and copying over with the parentheses correctly, but I got it to work so that it would have this guy, and here we have our 9 plus 2, and that was able to then go through, call find lambda again, and it got us our answer. So I am going to show you now, because I'm running a little bit low on time. This is an example of a lambda. This is how we're taking our lambda, and it's lambda x, so it's in terms of x, and we're going to have our operation is going to be multiplication. We have 2x, and so that is going to take an argument of 3. So 3 is going to be the lambda substitution. So this should get us 2 times 3. So I'm going to run this, and it did. It says first lambda because theoretically this could work for nested lambdas, so I only wanted to include, so this was just a print of the first one, and then, so this is our final answer. So let's see. This time we went to our main, and it did find a lambda because it found the letter L. So then it goes through, same logic, it goes from right to left, finds the leftmost L, not the leftmost parenthesis, and then goes up, saves what's to the right of it, and saves what's to the left of it. So the right of it is what we're going to work with. Ooh, yeah, okay. And then, so we call find lambda. The last, I have a correction to make, the last function we called was read input. That's where we were looking. I just called it find lambda. I'm realizing that now. So this is find lambda. This is with our lambda expression. So it goes through and let's see, saves everything to the right of it, and then so we look for our first right parenthesis, and then we save the next index is going to be our substituting value for all of our x's. So then right here, every time we find something that's equal to the value that we're going to be substituting, so every time we find an x, we're going to replace it with a 3 and then do the work. So this is where we're saving our first and second argument, and let's see, yep, so we have our first and second argument. In this case, they're going to be both numbers, so it prints accordingly. You can see this is the same as the code we were working with before, and it printed out the answer of 6. So what I want to detail, because I'm running a little low on time, is if I was to take this as a y, and for some reason I screw up and I have to get rid of that last parenthesis, that was a mistake, this would get us an answer of 2y. And the reason we have 2y as our answer is because 3 can't substitute in terms of x, because there's no x variable to substitute with. So the last thing I want to show you before we run out of time is, I guess I don't need to be freaking out that much about making 15 minutes. You said in class today that it didn't need to be exactly 15. But okay, so we get how that's working so far. So say we took an expression like 9 plus another lambda. So we're going to do 9 plus this second lambda. Oops. Okay. So this is the way this is going to work. Is it's going to go from right to left, and it's going to take this lambda to the right, lambda x. It's going to substitute in the 3 for the x and do 2 times 3. So that should then break down to lambda x 9 plus, and then the answer of 2 times 3 is going to be 6. So this should get us a final answer of 15. And so, oops, where'd it go? I'm going to execute that now, and we'll be able to see, and it's based on the same logic as the, yep, there's our answer, 15. It's based on the same logic as the operational small step semantics, in the sense that we went through from right to left, and we found our post lambda, which is everything to the right of the lambda. We solved that, then at the end, so we just went over how we solved that, we returned our lambda answer. So because this is in a for loop, we then take that lambda answer, and you can see I did a little bit of formatting here where I added that answer to the lambda, to like the existing. So I took the pre-lambda expression and then added my answer, and then I added a couple parentheses because I'd lost that, and I just had to get that corrected. So now we can call find lambda again, and that's going to take our new lambda, which is actually here. It's 9 plus 6. It identifies it and prints it out, 9 plus 6, which is how we got 15. So that's how my ISWIM interpreter works. We could also run this again just to prove that it works. We could say 9 times 6, and that should get us 54, which it does. So that's how my lambda, my ISWIM interpreter works. So the concept that I was most proud of working with this was the fact that I was able to get it to work for nested lambdas, and that I was able to understand how multiple functions can work together to find one actual main function. So like, for example, I'm not going to run it, but if I had like lambda x, you know, and I'm doing 2x, what was I going to say? So let's say I did, let's say I did 9 plus, and then another lambda x, 2y, 3. So this would be an example of 3 doesn't substitute for y. So we would end up with 9 plus 2y as our final answer for this. And that was interesting to me because I was able to take this long, foreign-looking lambda expression and break it down into something that I knew and something I would be able to work with. And so what I found the most challenging about this whole thing was I wanted to attempt to do it in terms of the machine, but I didn't know how to do that, because I get that it was supposed to work sequentially from right to left, from like innermost parentheses to outermost in a sequential form of functions to be able to get some kind of answer. But I didn't know how that would interact with the machine versus, I don't know what would be different about what I did versus what a machine would do, because I didn't know how to represent the continuations and break it down into smaller sections. So that was something I would have liked to have got done. And besides that, I think that might be it. I've gone a little bit over time. Thank you very much for listening, and I'll see you for the final. Thanks.